Good afternoon, everyone. I'm Divya, and my teammates are Anjali and Arya, and we worked on the project Gesture Control Augmented Reality under the guidance of Professor Preet Kanwal. Next slide. Coming to the introduction and abstract. So, the problem we are trying to address in our project is the genericness and accessibility of augmented reality applications with gesture recognition. So, in recent times, I think everyone would have observed that the relevance of hands-off access to technology has been increasingly popular because of the COVID-19 pandemic. And it has become a necessity to integrate augmented reality into daily life. And even though the technologies and techniques in augmented reality are uh, evolving every day, the integration into daily life has been slow because most software applications do not have a compatible AR interfacing system. And in addition to this, the use of AR technology usually requires many expensive and inaccessible hardware devices like head mounted devices or special cameras like depth sensing cameras. And with all of this involved, it becomes a very high processing overhead along with being expensive and uh, further, you know, doesn't encourage the integration of AR technologies into our day to day life. And natural and intuitive gesture controls on three-dimensional AR objects are almost impossible to run on everyday smartphones that is available widely. So in our project, we are aiming to propose a methodology that will allow us to use a generic and accessible gesture controlled AR platform for everyday use. And in this, the platform would control a PC remotely via hand gestures that are made by a user on the interface. And the application is very generic and not specific to any use case. And we're doing this by making the AR system provide an AR interface on any application that can run on a regular PC. And the AR application would work on any smartphone with a regular RGB camera, and this will this will enhance the accessibility of the platform. And because of this, we don't need any external hardware devices which is usually required for popular toolkits like AR and AR Core and AR Kit. Next slide. Coming to the design approach and implementation, which we will start with the summary of the literature survey. So the first paper that we looked into as part of this project is hand gesture recognition, a literature review. And in this paper, the different gesture recognition algorithms, pros and cons were discussed. So how our project would differ is that we do not use any ML algorithms for gesture recognition, and instead we are using mano motion or computer vision algorithms. And the next paper was natural interaction in AR context. And in this paper, the types of gestures that are used in gesture recognition systems like translation, scaling, and rotation are discussed. And in our project, we wouldn't be using these gestures, but would keep it limited to basic hand gestures. So another paper which we looked into is Markerless 3D gesture-based interaction for handheld AR interfaces. And in this uh, paper, mainly the methodology for segmenting the user's hand from the surrounding was discussed and the ways in which we can manipulate virtual objects via gestures. Again, in our project, how it is different from our paper is that we are not using any depth sensing camera used on top of the actual camera, and we are only using the regular RGB camera that is present in most smartphones. Next slide. The fourth paper that we looked into is hands in space, gesture interaction with AR interfaces. And in this, they discuss a client-server system setup, along with the basic gestures that users are most likely to use while manipulating 3D objects. Also, depth and image recognition and tracking in 3D object manipulation was discussed. So how our project differs is that the leap motion controller and external depth sensors like Kinect for object tracking will not be used. And instead of that, we would be using small marker images like a QR code or make the application completely markerless. So the next one is study of gesture recognition methods and augmented reality, which discussed an AR application oriented approach to gesture recognition. And how our project differs is that AR system integration will be incorporated, which is not explained as part of this paper. And the last one is Introduction to Augmented Reality, which was a generic paper discussing the complexities of an AR system and how important it is to have a good interface in these systems. Um, in our project, we will be exploring gesture recognition as well, but which was not covered in this paper. Again, as mentioned earlier, we won't be using any external devices and we will retain the real objects in the environment as well. Next slide. Coming to the requirements and design and starting with the hardware requirements, during the deployment phase, we just required an Android smartphone with an RGB camera, which had a moderate to high processing power as well as a moderate to high storage capacity. And during the development phase, we required a 64-bit computer system, which was supporting the latest versions of Unity, as well as an Android smartphone for debugging. Next slide.
Coming to the software requirements of our project. So the first software requirement would be Unity and C#. So Unity and C# is the associated coding language for Unity, and this would be needed for setting the environment and creating the augmented reality platform. Vuforia would be needed for image databases and corresponding image tracking. We would need Blender to make the low poly models, and the Android and Java would be needed to port our application to an Android smartphone device. Python or C++ would be required for external computer vision algorithm implementation, like those for gesture recognition and depth perception. And Nanomotion would be used for the initial gesture recognition. And AR Core would be required for depth recognition, but we haven't really used it because of the very limited number of supported devices. And finally, for communication interfaces, we would need a stable internet connection for communication across our personal computer and the AR application which is running on a smartphone. Coming to the functional requirements of our project. So the first functional requirement is that the virtual object, which is the augmented screen in our case, would need to be placed at the correct location. And then the hand of the user would need to be calibrated along with the position of the hand would need to be detected. And then to recognize the gestures, first the movements of the user's fingertip would need to be identified, followed by the recognition of the gestures. The captured gestures would then need to be translated into commands which are understandable by the computer, and these commands would need to be sent to the backend application. Then the commands would need to be actually performed on the actual backend application. And then the state of the application after performing the commands captured from the gestures would need to be returned to the AR application running on our smartphone. And then the changes corresponding to the commands captured from the gestures would need to be rendered in the AR environment. Moving on to the design constraints of our project. So the project is mainly constrained to be deployed on an Android smartphone with a RGB camera. So for the proof of concept of purpose, the application will be limited to a browser running on a remote personal computer, but it could be ported to any interface. And the security and optimization are beyond the project scope, and the user would need to ensure his personal safety and security while using the AR application. But from our end, we have ensured that all sensitive data stored on our server would be flushed on exiting the application so that there would be no threat posed to the user's privacy and security on using our AR application. And lastly, the user would need Python 3.5 version or above to be installed on a new device in order to set the new device up while to be used with our application. Moving on to the design assumptions that we made while developing our application. We first assumed that the user would have all the required hardware and software capabilities to support our application, and the user would need to be technologically aware and should have the desire to incorporate new ideas. The browser application would also need a proper internet connection, and finally, to recognize the hand gestures performed by the user, we would need proper lighting conditions and smartphone orientation so that the right gestures could be captured and translated into commands to perform manipulations on the virtual object. Moving on to the risks of our application. So there are actually no application risks while development and deploying. However, one potential risk of using our application could be the possible physical harm that could be caused with the user's lack of attention to his surroundings. So this is similar to the cases reported against the augmented reality technology development in itself because of the accidents caused while playing augmented reality games like Pokémon Go, which are again caused by the user's lack of awareness and the lack of attention to his surroundings while using these applications. Um, Moving on to the possible approaches and design choices that we had while developing our project. So for our AR interface, for developing our AR interface, the two major choices that we had were whether we had to use the Unreal Engine or the Unity Engine to develop the AR application. So the Unreal Engine provided stronger game engine features and rendering quality, but the Unity Engine provided a platform to build applications that could be made portable across a wider range of AR devices. So for developing a project using Unity meant that the application could be compiled for generic devices like regular smartphones, as well as advanced devices like augmented reality, head-mounted devices as well. So for this purpose, we chose Unity over Unreal to develop our AR application. For the gesture recognition part, we could implement it by using ML-based models or using motion as well as static gesture recognition. So for the ML-based models, they are very slow and heavy, but they could support a wider range of gestures. Motion, on the other hand, although it supports production quality gesture recognition, it is not compatible with all smartphones. Whereas static gesture recognition, on the other hand, could only support a limited number of gestures, but it is very quick, responsive, as well as portable. So weighing the pros and cons of all the options, static gesture recognition was finally chosen for the demonstration of this project. And finally, for the system integration part, we had two choices. We could either go ahead with client-server system or a cloud-based system. So client-server systems, in spite of them being fast, they are very limited in the sense that both the devices, which is the remote host PC and the smartphone, which runs the AR application in our case, both of these would need to be connected to the same network, which would restrict our application. And cloud-based systems, in spite of them being slow, the devices could be on different networks, which would give us more flexibility. So we chose cloud-based integration for this project. Moving on to the next slide. Over to Arya.
Yeah. So the overall design description, as Anjali had stated in the previous slide, has three main components to it. The AR interface, the gesture recognition, and the system integration part of it. So the first part of the project is the augmented reality. In this part, the AR environment is provided to the user as an interface, and this part has to be rendered and defined by us. The challenges involved here were being able to place the object in the real environment, finding the optimal resolution in which it has to be rendered, so that it's not heavy on the battery life of the portable device. At the same time, it should look realistic and blend in with the environment, so we have to retain the outer world objects also. Then the second component, which is the gesture recognition system. Yeah, this is where we define the gesture recognition algorithm that we need to use. And we have currently restricted it to identify a limited number of basic gestures like changing the tab, scrolling, clicking, etc. Then the system integration, which is the last part. It's the most essential part, and it runs parallelly along with the AR interfacing and the gesture recognition components. So it has two main parts in it. One is the integration for remote browser manipulation, and the second is the integration for the gesture recognition. So for the remote browser manipulation, this part focuses on how the AR application has to interact with the host system to update and sync changes in the in the application. And the part with the integration for the gesture recognition focuses on how the AR application has to interact with the remote server to recognize the gestures. Both these parts are currently intended to be have been resolved using Firebase, and the states and the changes are recorded in Firebase, which is accessible by the host, the server, and the AR application. And this is also the reason why a good internet connection is required during runtime of the whole project. Moving on. The the major details of these particular steps are the following, like which I mentioned. So the first one has the basic marker-based ER application, then integration of the external code with Unity, depth, dynamic depth fixing, and similar such processes involved in developing the whole three components. Um, then following towards, then going towards the sequence diagram. So this is how the entire flow of the system works. So the process begins with the user enabling the host PC to be accessed by the augmented reality application. Then this is automatically followed by the storage of the initial state, and we define the state as the screenshot of the entire PC in this case in the Firebase cloud storage system. Once the user opens the AR application via the user's smartphone remotely, then the state of the host PC is fetched from the Firebase cloud storage and rendered as an AR interface in the mobile application. Uh, then, as the user maneuvers through this AR interface, the state, which is again the screenshot of the AR environment, is also stored in a separate storage in the same Firebase cloud storage system. This picture or state of the AR environment is constantly monitored by the gesture recognizer now to identify the uh, to identify any gestures shown by the user. Once the gesture is identified, it is updated in the Firebase RTDB, the real-time database now, instead of the cloud storage. And the host PC reads the gesture from the Firebase real-time database and updates the state of the remote PC. The new state is again updated in the Firebase cloud storage, which is reflected in the AR application, and this cycle keeps repeating. So the main users in this, yeah, yeah. So the main users in this whole system are the host, which is the remote PC, the server, which is the gesture recognizer, and the controller, which is the AR application. Each of them have like various functions and is independent of each other, which makes the entire system flexible for each component or subcomponent to be replaced. Yeah, over to Anjali.
Okay, coming to the implementation details. So beginning with the augmented reality module. So this augmented reality application module acts as the controller of the entire system. And in this part of our project, basically improvement in the accessibility of AR applications and their users targeted. So this our application is deployable on a smartphone rather than a head-mounted device due to the larger availability of smartphones and ease of access across the world. And also our smartphone would only our application would only require a regular RGB camera that is built into a standard smartphone without the necessity of a camera powered with with pre-existing depth sensing technology. And since most AR applications use AR Core and AR Kit, which require smartphones with a depth sensing camera, our project challenges this popular standard. The design choice of choosing Unity as a development engine over the Unreal Engine was a conscious move to make our AR application deployable to a broader spectrum of devices and not restricted. And however, this choice had to make a compromise on the larger feature set and the stronger and more robust engine that Unreal would provide. Coming to the implementation details of our remote host. The remote host is the actual backend personal computer that is being manipulated with our augmented reality application. So the genericness of our system would be demonstrated in this part of the module, as any application visible on the remote PC screen could be replicated as a holographic AR screen, and then the PC could be controlled via gestures using an AR application at any remote destination, provided it has a stable internet connection. So for the proof of concept of our project, a browser application which is running on a remote PC is being manipulated by using our AR application, which is running on a smartphone. Over to Divya.
Coming to the implementation details of the gesture recognition module. So the backend server runs the gesture recognition system, which is the host PC in this case. And we made a design choice of using a static gesture mapping because the recognition can be quick. But one challenge that this poses would be that not many gestures can be supported due to the static nature. But however, the speed benefit outweighs the reduced number of gestures that are supported. And another option would be to integrate the gesture recognizer in the AR application itself, but this would have to run in the smartphone and hence would lead to a lower processing power. So as mentioned, the external server, which could be the host PC, will run the gesture recognition system, and that majorly involves two parts, which is the hand segmentation, or separating the outline of the hand from the rest of the surroundings. And the second part is the recognition of the gesture in itself. And for segmenting the hand from the surroundings, there are three steps, which are background subtraction, thresholding, and contour extraction. And for recognizing the gestures, or the steps that were involved were first computing the extreme points of the hand, such as the tip of the thumb, the tip of the middle finger, the tip of the pinky finger, and the base of the palm. And the next step is to find the center of the palm and to construct a circle around the palm and the fingers. And lastly, a bitwise AND has to be performed between the hand region and the circle that we outlined earlier over the hand region, and then this is used to determine the count of the fingers. Next slide. Coming to the implementation details of the storage and communication. So here we are handling the storage using the cloud storage systems, and an alternative way to handle this would be to use a client server system. But the client server architecture is restricted to application, their application to run on the same network as the host PC. And this could be a clear disadvantage in our case, since we needed both to be on different networks for remote functioning as well. So in our application, we are using Google's Firebase cloud system for all the storage requirements. And Firebase real-time database, or RTDB, is used to store the recognized gesture that is identified by the gesture recognizer backend, and this is immediately used by the remote host to update its state. So here the screenshot of the gesture is taken, and here's the state refers to the state of the remote PC after manipulation. So the Firebase cloud storage is used to store the host PC's current state, which is used for updating the AR environment, and the AR environment which is used for the gesture recognition. Next slide. Over to Arya for the testing.
Yeah, so coming to testing, we ran the following testing. So in unit testing, we had the black and white box testing. Integration in integration testing, we did the incremental integration testing, and then system testing, the usability testing. And the following were the test results. Could you move on to the next slide? Yeah. So in the black box testing, the user interface was basically tested out, and then the UI is simple and sufficient for the demonstration, and the inputs giving the desired outputs, and yeah, it was working fine. Then white box testing. Sorry. Yeah, in white box testing, the gesture recognition was primarily tested here. And the gestures were recognized accurately and are also easy and intuitive to perform. Then with for incremental integration testing, so there were three components to it, which is the AR with the cloud, GR with the gesture recognition with the cloud, and the integration between all the three components. So yeah, so initially we had like Firebase permission issues with the AR with cloud integration, but they were fixed. And it works fine now. And the gesture recognition and the cloud systems work perfectly fine. And with respect to usability testing, we focused on two main criteria. The first one was extensibility and flexibility, and the second is the latency. With respect to the extensibility and flexibility, since we made the whole system as a collection of tiny subcomponents, and each component can be replaced by any other component that the user desires. For example, for the gesture recognition, if the user wants like a different set of gestures or a different gesture recognition algorithm, it's easy to just substitute that one component. So it's highly extensible and flexible. And latency, there was an initial lag observed for certain gestures, primarily due to the cloud syncing and the internet connection time. But yeah, it was resolved to a large extent. Then coming to the results and conclusion, yeah, the proposed methodology was applied on a browser system, yeah, which is Google Chrome and Microsoft, like all browsers used to work with this application that ran on the laptop with an internet connection, and it was accessed using an ER interface on an Android application, which was connected to a separate network. Syncing had minor lags and it depended on the internet connection of both the devices, the PC and smartphone. But the proposed methodology gave a simple, generic, highly accessible solution for AR interfacing for any application. And conclusion and future work is that, yeah, we developed an AR application that could be deployed on an Android smartphone, on any basic Android smartphone. Then basic gesture recognition was employed on the server, and the AR application works as per the gestures specified. The application can be used from anywhere, like since it's independent networks. And the future work that could be done is that we could provide functionality to support more gestures and also improve speed and performance over time. Yeah. This is the documentation for further reference. And these are the references that we used um, over the course of developing a project. And thank you. Yeah, this is the team behind the project.